Hello students, in this module we will discuss now the non-coherent systems. Basically target is to see that for non-coherent communications whether how do we dissipate the signal and whether match filter architecture that we have already discussed in the last module is equally applicable here, or do we need actually to put some separate synchronization block here to realize the system implementation. And if question is what will be the error probability at last of this non-coherent system using match filter in the receiver, such that actually there is a loss or there is a not a loss at all compared to the coherent communication systems. So, we need to understand all those points. Question number 1 that it will be clear is whether you can apply the match filter structure alone without incorporating another synchronization block for code acquisition and code tracking for non-coherent systems or not. If the answer is yes, then with this structure, with the match filter structure, what will be the error probability, how it will be derived and what will be the expression for the error probability. Then the question is in terms of the when we are computing the error probability, whether there is a loss involved, are we losing in terms of some dB value in the SNR compared to the coherent communication system or not. If it is yes, then how much is it? Okay. Let us start. A non-coherent communication system. The first figure is showing a typical block diagram of the transmitter of a non-coherent communication system. So, data bits are coming both in the upper AND gate as well as in the lower AND gate, and it won't be like this, it will be basically it will be not going inside like this, it will be going like this. So, the data bits are coming, this is not true. So, the data bits are coming like this, and spreading sequence generator, there are two different spreading sequence generators, and the clock is triggering both of them, but depending upon the clock sequence, actually either any one of them, one of the sequence generator will be activated and output of this sequence will be fed as another input to the AND gate. So, AND gate is receiving the data bits and he is receiving the corresponding spreading sequences. So, remember as we have shown two different spreading sequence blocks. So, one sequence is dedicated for the symbol 1, another sequence is dedicated for the symbol 0. That is why already we know, right, that codes can be utilized for modulation also. So, here we are seeing that code is modulating the data bits. So, that is why it is a code shift keying. So, for each and every data symbols you are using different spreading sequences, and remember at a typical instant either module 1. So, based on which generator is actually activated for what kind of the data bits coming, then either at a particular instant the module number symbol 1 will go or otherwise symbol 0 will go. So, either the AND gate 1 will be high, output will be high, or AND gate lower AND gate output will be high. Both the outputs are getting ORed, they are added in the OR gate structure. So, once they are added here, so any one of them will be actually allowed to get transmitted. So, at a particular moment we understand by this structure that based on the choice of the codes and based on the data stream that is coming, actually either upper sequence generator or the lower sequence generator is getting activated, and then actually corresponds. So, each of the symbol is getting spread by the unique codes. The code for the 1 and code for 0 are different, and at a typical symbol either the upper AND gate output will be high or the lower AND gate output will be high, and they are getting added inside the OR gate, and either at a particular instant t, either the symbol 1 is getting transmitted or signal 0 is getting transmitted. This is the structure of the transmitter. Let us see how the receiver looks like. The CSK, some few more information left with respect to the transmitted figure. Remember that in absence of this noise and the interference, each sequence will cause only one envelope detector. That actually in the figure 2, let us go and come back, because otherwise it will be hard to understand some more points that is explained in this typical slide. So, let us go forward and understand the receiver structure. I will come back to the previous slide. See, in the receiver, I understood that the signal is transmitted at a particular time moment, either I transmitted 1 or I transmitted 0 with the proper choice of their code associated with them. The received signal is received by the wideband filter, and that wideband filter output is now matched to the they are having a two different path in the receiver. So, the match filter impulse response of the upper one and the match filter response of the filter 2, they are not same. Actually, they are basically matched to two different kind of the signals. So, one signal dedicated to say symbol 1, the upper one say dedicated to symbol 1, another one is dedicated to symbol 0. So, each of them are matched to, we sent two different sequences, right, from the transmitter for symbol 1 and symbol 0. Here also we have designed two different match filters matched to each of them. So, remember at a particular moment at the output of the wideband filter, though it is fed to both of them, at a particular moment based on the signal with which actually the filter is matched to, either the filter output 1 will be significant or filter output 2 will be significant. The output of this filter is fed to the envelope detector. This envelope detector is the way we have seen in the previous module, that match filter followed by an envelope detector is the best option to implement synchronization without synchronization receiver architecture compared to only match filter and then picking up the peak of it. We understand also that there will be a loss, but that loss is not that much significant at all, and it can be easily implementable also. This architecture is easily implementable also. So, we henceforth we will go ahead with this match filter with envelope detector output, and as we understand that compared to followed by the match, any one of the match filter output high, any one of the envelope detector also will be high. So, the summation of the both envelope detectors will give actually me the output, and this summation will be actually the output of these two envelope detectors will be doing the also triggering the symbol synchronization, and the comparator network will be comparing both of them, and the synchronization will be coming into picture with two synchronized upper envelope detector signal and then lower envelope detector signal. So, question is actually why we have done here actually added here the symbol synchronization. So, before coming there to give any explanation, let us go back little bit, and the points that we left in the last slide, let us finish it off. So, what we are left here is that see, if the noise and the interference they are absent. So, each and every sequence will for every sequence will cause only one envelope detector to produce the significant output that I have already told, and data will be recovered by comparing the two detector, that also we have discussed seeing the architecture. And since each of the two orthogonal sequences who are also sequences who are orthogonal to each other, they have a period exactly equal to the symbol duration. So, in the whole architecture of the noncoherent communication system, the synchronization basically means a symbol synchronization. So, code synchronization as well as symbol synchronization, they are identical. So, you do the symbol synchronization, automatically code synchronization will come into picture. because you have utilized the orthogonal codes. Your data bits are basically modulating the orthogonal codes 1 and 0, the data, they are modulating two different orthogonal codes. So, the modulation is done at the rate of the symbol period. That is why the modulated symbol will be also having the period is equal to the symbol duration. So, in the received signal after the match filter output and the envelope detector. So, if you try to do some synchronization left, so that will be basically a symbol synchronization. There is no meaning of telling it is a code synchronization. Even if you call it as a code synchronization, they are synonymous. So, with that actually for the remaining synchronization, so the symbol synchronization block will take care of the fact, and the comparator device is finally going to compare both of the outputs envelope detector 1 and 2, and finally giving a hard decision about which beta bit was transmitted, seeing actually from where actually the maximum output is coming. Based on that, he will give the output of whether the decision of whether the message bit 1 was transmitted or message bit 0 was transmitted. Now, the symbol synchronizer that we have seen in the last slide, this which provides the timing pulses. It is a symbol synchronizer. So, start point of the timing, where the symbol start point is, he will intimate and to the comparator or the decision device, and this synchronizer also should lock the instant once actually it is detected, and it will declare also that perfect lock, and it should try to lock when the autocorrelation spikes are coming in the envelope detector outputs, and this spikes, if you try to see that the spike that actually output of the envelope detectors are giving you, that will be a shape of a triangular, and so it may happen that actually if it is depending upon the sharpness, definitely actually you will be able to detect this moment or this instant very precisely. The symbol synchronizer must be impervious to the autocorrelation side lobes peaks and any cross correlation peak lobes, because though we are expecting that something like that is expected, but remember the shape of this autocorrelation, as we have learned, it heavily depend upon the kind of the code you are choosing. If it is an random binary sequence or ML sequence, you can expect actually that this kind of the triangular shape is expected to come at the output, and then your choice of the locking, because if the peak is sharp, your choice of locking or finding the perfect instant will be very easy. Think of a situation whether when the peak is like this and the autocorrelation side lobe is also having a very high peak compared to the main peak power, then the synchronization may get false locked in the previously appearing one, or if it misses the peak to detect, it may declare that the lock should be here. So, synchronizer, the algorithm that you are designing for the symbol synchronization, it should be aware of the autocorrelation pattern of the selected sequence, and the algorithm should be such that it should be precisely identifying the autocorrelation main lobe peak. On the contrary, if it is the cross correlation peaks that he is defining on, or he is relying on, in that situation also the side lobes of the cross correlation is playing a very important role, and comparable high peak in the cross correlation side lobes may give you actually the wrong detection points. Synchronization algorithm should take care of that. So, algorithm should be devised in such a way that most of the time you were getting locked on the main lobes peak. A very simple implementation, that how will you do this symbol synchronization, is with a single threshold detector, and whenever the detector you put a threshold, actually you know what is the maximum side lobe powers, you put a threshold above that. So, whenever the power is accumulated power is crossing that, you declare that there is a peak, and But if you are doing it with a very single detector kind of, it is the easiest one, but if you do it with a single detector, you may result in also the some false alarms, because see, when if the curve is not very sharp and if it is having some slope like this, if it is a main lobe is having some slope like this, say, and this is the level of your detector single level detection threshold. So, once actually the threshold is crossed, it will be synchronizer will tell that this is there is a lock, whereas it is a wrong detection, because your peak is actually having say T 0 apart from this initial one. So, sometimes it may give you some unacceptable number of the false alarm, premature detection, or it may also give you the misdetection to some extent. So, people prefer to have actually the multiple threshold based detection, and when the received amplitude is unknown and has a very wide dynamic range also. In that situation, basically depending upon one threshold detector is not at all a good suggestion to proceed with. And there is a easy way to control that problem that we have discussed earlier. What we can do, that we can actually control the automatical gain control AGC to reduce actually this to resolve the problem, but only the problem is that when that is below that the whole stuff actually the controlling the automatic gain control will automatically again may lead to you the false point lock, when the signal power level will be below the interference plus the noise level. So, it is low value of interference plus the noise. The problem is also not good to resolve it by the controlling the automatic gain control power gain control voltage. So, more than one threshold detector is a good choice, and with given the highest threshold crossed will improve always that the accuracy of the decision timing, the sampling instant produced by the symbol synchronizer. So, all those points, the accuracy of the decision timing or the sampling instants which are produced by the symbol synchronizer, all of them, both of them basically will be improved. Another approach is to what? Is to use peak detection based on the differentiator or the zero crossing detector. Peak detection algorithm can be also used on the differentiator as well as the zero crossing detector based, because without actually fixing only the single based threshold, only the single threshold, and actually trying to compare it what exactly is going on with the declaring the lock once immediately after crossing the first threshold level. Instead of doing that, if you wish to detect only the peak, then there is a differentiator. That means, each and every moment you keep on changing, keep on checking the sample value, the current moment's sample value peak as well as the previous moment's sample value. So, if you see actually that there is a continuous increment happening, so you keep on going on before actually declaring the peak, and you do the declaration once actually this difference is instead of increasing there is a decrease. Or sometimes we go ahead with a zero crossing detector also. But finally, above all this, a phase locked loop or a feedback loop is the best option for the symbol synchronization. And whatever be the situation for the symbol synchronization, we usually prefer to send training sequence inside the preamble of the data in the packet structure that we have earlier discussed. If this is a packet and this is a preamble, we will send actually some known training sequence inside that preamble to help the receiver in the synchronization process to establish, because in that situation the receiver will have the knowledge of the replica of the sequence that is expected to come. We call it a training based synchronization. Sometimes we prefer not to, but this training based synchronization will give you high accuracy in the synchronization process, but there is it is not spectrally efficient, because this is a training data, this is not your useful data that you are transmitting, this is a training data that you are transmitting, and this is a wastage of the bandwidth also in that sense. So, it is not spectral efficient, but synchronization accuracy wise this is the best way to proceed. Another way that we usually prefer is the blind estimation synchronization technique, where we do not transmit anything like this from the transmitter, but what we try to do is seeing the pattern of the extracting the statistical, we try to extract the statistical property of the received data symbols and try to devise our synchronization process from the received data symbols itself, try to extract the estimate the timing estimation and timing information from the received data or received payloads. Another is data aided, where actually the training sequence is sent as well as the detected data output is fed inside the synchronization block, and then jointly actually this is a core synchronization when training based is going on, and the data aided portion further enhances the synchronization point. We call it data directed or data aided. Under the data supported by the data section, it is a synchronization process. Another one is. So, now consider the detection of a symbol which is represented by this expression. So, this is the received symbol that we have written here, and we understand this format we have seen in the last expression in the last module also. P1t is the one period of the signal getting transmitted of the code sequence, T0 is the delay, and F1t is the received frequency, received signal frequency, and capital A, we understand the polarity of the capital A will be governed by the data symbol itself. This is the period of our interest T0 to T0 plus capital T, and this P1t, this is the CSK waveform to which my filter 1 in the receiver architecture. Please refer the receiver architecture block diagram once more. Matched filter 1 was actually on the upper path, and filter 1 is matched with this P1t. So, following actually the last expressions that we derive for the match filter based dispersing process, we understand that YST can be approximated as AST into cos 2 pi FCT plus theta 2, and the envelope detector output, this is the match filter output, this is the match filter output, and envelope detector output also going by the expressions that we have derived in the last module. It will be ended up with AST plus N1 t square plus N2 square t. And we also understand that in certain situation this N2 t portion will be deleted, approximately deleted also if the for certain situation. And we also understand here that with t, capital T is equal to T s and T0 is equal to 0, we find that the output of the envelope detector 1 at your T is equal to T s, this will be given by R1 is equal to Z1 square plus Z2 square whole to the power half. So, envelope detector just discard this to number, that envelope detector output or envelope detector at the point 1 at T is equal to T s is always given by the Z1 square Z2 square square root of it, but what is this Z1 and Z2 we will explain in the later slide. The Z1 is nothing but the intended signal section plus over the point of the interval, interested interval. It is a noise that is spread by the sequence as well as multiplied with the cos function of it. Z2 is nothing but that noise, but this is a contributed energy part, noise contributed over, and this is the orthogonal part, noise on the orthogonal, another orthogonal part. And similarly, if my filter 2 is matched to the sequence P2T, then again we will get the output of the envelope detector 2 is given by Z3 square by Z4 square, and which having some similarity with the previous one. and Z3 will be given by this expression, whereas my Z4 will be coming out of this. See, actually the response to the transmitted symbol at t is equal to T s will be typically 0 because of the orthogonality of the sequences. And suppose that the interference plus noise is modeled as a 0 mean and Gaussian interference, and the spreading sequences are modeled as the deterministic and orthogonal, then where are we? Then remember that expected value of this Z1 you will be actually ATS, because see, come back here, this Z1 is written by this. So, if I take the mean value of this Z1, this is the noise section which is modeled as a 0 mean Gaussian random process. So, the mean of this whole expression will boil down to here, and Z2, Z3, Z4 they are actually for I is equal to 2, 3, 4. For all that the expected value will be typically 0. So, if NT is assumed to be the wideband enough and its autocorrelation function is approximated by this, we have seen it earlier also when we were declaring the first time we were discussing about the DSSS receiver architecture. Then the straightforward sum straightforward calculation here, which uses the FC into Ts greater than equal to 1, orthogonal property of P1 2 and P2 T, that we understand that all the noises that are getting added in the path number 1 as well as in the path number 2, I mean the noise associated with Z1 and Z2, Z3, Z4, all are the other components of the noises, all the noises are they are uncorrelated with each other. And the jointly Gaussian character of the random variables then implies that they are statistically independent of each other also, and hence R1 and R2 they are independent. So, if we can find that here and this guy, so these two are now proved to be completely statistically independent to each other. So, similar results we can have with P2T, where actually the discussion will be such that the Z3 will be written as ATS plus this, and Z4 will be having this expression, where Z1 and Z2 will have only the noise part. And similar outcome will be there also, and you will be able to see that R1 and R2 are again becoming statistically independent, essentially independent, considering that the noise samples are 0 mean Gaussian distributed. So, understanding both the path like this, a straightforward derivation is also possible for the error probability calculation, which will be governed by this, and this expression we have seen earlier, where your NOE will be given by the known expression that we have seen in the module 17 for the Gaussian considering the Gaussian interference is coming on. And now you compare these two expression. Which two expression? One expression is this one traditional one, the non-coherent communication system. Another is the coherent communication system. A straightforward comparison will show that a non-coherent binary CSK system will have approximately a 4 dB worse. The performance will be approximately 4 dB worse compared to the direct sequence spread spectrum systems. So, what is the meaning of it is, if you wish to get same error probability for your non-coherent CSK system, you have to provide 4 dB extra transmit power to achieve the same error probability, same bit error rate as compared to the coherent communication system. And this difference, how does this difference arise? This difference arrives from the fact that in the CSK we use orthogonal sequences, we do not use the antipodal sequences. Usually for the coherent communication system, we use the coherent communication system, we use the antipodal sequences and antipodal or orthogonal, not the orthogonal waveforms. It is antipodal signaling basically. Complicated, a little bit complicated version of both this transmitter receiver that we have discussed here, and that if we complicate it little bit more, it is possible to show that this 4 dB loss can be improved little bit, but that also will increase the hardware intense some system design, and we can come up to a gap of approximately 1 dB. So, from 4 dB to 1 dB. So, 3 dB compensation is approximately would recover roughly around 1 dB. So, 3 dB loss is not to be recovered around, still 3 dB loss will be viewed. And now, the another extension of this understanding with Q array CSK encoders, that from each group of m binary symbols, as one of the q equal to the power m sequences, it will be chosen, and that sequence should have a very negligible cross correlation values for Q array CSK transmission. And suppose if there is a bandwidth constraints that limits the chip rate of this binary CSK system to say g number of chips per data bit, and for fixed data bit rate, if your QCSK system produces small m into capital G number of the chips. So, you can think that each group of these m bits, which may be regarded as a single Q array symbol, which can be regarded as a single Q array symbol, the processing gain relative to the data symbol will be m into G, will be simply m into G. And this indicates that there is an enhanced actually processing gain, and it is having an enhanced ability to suppress the interference also. And we have seen that in the presence of our wideband Gaussian interference, this performance improvement with your quaternary CSK system, I mean this is equivalent to the our coherent QPSK, actually the data rate wise, and it will have more than 2 dB requirement compared to the relative binary CSK system. And 4 filters match to the 4 double length sequences. I mean, you see the structure, the way it will be complicated definitely for the higher modulation schemes, and 4 double length sequences should be required there. When the chip rate is fixed, so Q array CSK provides a means of increasing the data rate, data bit or the code symbol rate without sacrificing the processing gain. And if I now eliminate this lower branch of this figure number 2, yeah. So, if I discard this total branch of this 2, so it will give you the single carrier CSK system, and you can proceed actually of calculation of the error probability for this single array CSK system. And in that situation, your signal 1 will be transmitted with some signal, and no transmission means it will be a symbol 0 getting transmitted. The output of the envelope detector, try to see what exactly is coming out. If it is close to the noise levels, he declares that it is so comparator declares that it is a 0 signal transmitted in that situation, and if it has some meaningful value and it is crossing some threshold also inside the comparator, the output of the envelope detector is crossing some threshold detector, then in the comparator will tell that the transmitted signal was 1. But one problem with this system is that the optimal threshold is a function of the amplitude of the received signal always, and somehow, and that this amplitude needs to be somehow estimated in lot of the situation. Another problem will be that the degraded performance that we are seeing as comparison, degraded performance will be also coming from the symbol synchronizer, when lot of the consecutive zeros will be transmitted, and thus system with your binary CSK is much more this is much more practical in the sense that you are getting actually some situation or some circuit architecture where your some extra load for the coherent communication can be avoided, but at the same time the performance with close to the binary PSK can be obtained with the match filter architecture definitely. And symbol synchronization, some little bit we have to put our effort, because that is playing some vital role inside this, and the loss that is that we have seen actually compared to the conventional communication system will be around your 4 dB, that can be further reduced by another 1 dB approximately. but below that, even if you are trying to complicate the network, complicate the system, further improvement on the VER is further improvement on the SNR SNR is not possible.